An AI satellite crosses the night side of Earth. Its payload computer sorts images before they reach the ground. Another computer keeps the satellite pointed, manages power and communications, and decides what happens when the AI system crashes. That computer may use a design for chips that is 20 years old. BAE documents the RAD 750 at 200 MHz, with first flights in 2005. So why does a modern AI satellite still need it, and can bleeding-edge chips survive long enough to justify the risk? The answer begins with the distinction that gets lost when people ask what processor a spacecraft uses. A spacecraft is not one simple computing job. Flight-critical avionics handle command, altitude, power, communications, navigation, and safe mode. They often care more about deterministic timing and a known response to failure than about peak throughput. If the main payload stops working, the mission may lose science. If the flight computer loses control, the mission may lose the spacecraft. AI and science payloads want something different: memory bandwidth, vector processing, high data rates, and strong performance per watt. Those are the strengths of modern and commercial AI-oriented architectures. So the advanced design is not simply old chips being replaced by new chips. It is a heterogeneous spacecraft with multiple types of chips. A proven controller can fly the vehicle. A newer processor or FPGA can run the AI workload. A hardened supervisor, watchdog, redundant links, and recovery software can keep the experimental compute from taking the rest of the spacecraft down with it. The old processor is not necessarily competing with the AI chip. It may be what makes using the AI chip possible. Why are those flight computers so conservative? Not because old automatically means reliable. Older architecture, older manufacturing processes, and larger transistor features are different claims. None of them is a magic radiation shield. The advantage is evidence. Space radiation can cause a recoverable bit error, interrupt a function, slowly degrade a device, or create a destructive event such as a latch-up. Engineers respond with layers: hardened circuits, error-correcting memory, lockstep execution, current limiting, watchdogs, redundancy, and safe mode. Then they test the exact parts, packages, boards, operating modes, and software against the mission's radiation, thermal, vibration, power, and lifetime requirements. They control manufacturing lots and configuration changes. They keep compilers, drivers, and test tools stable. Finally, real missions add flight history. That is why a platform can stay in service for decades. Its age represents accumulated knowledge about how it fails, how the system detects the failure, and whether it can recover before the mission is lost. This begs the question: can bleeding-edge AI chips work in space? And bleeding-edge chips can work in space. The harder question is whether the spacecraft can afford to trust them. A modern AI processor may deliver far more useful work per second than a traditional flight CPU. It can analyze images, detect events, steer a sensor, or reduce the amount of data that must be transmitted back to the Earth. That performance brings trade-offs: high power density, difficult thermal management in vacuum, complex memory and software, rapid commercial product turnover, limited control over manufacturing changes, and less radiation evidence for the exact device. A payload can be designed around those risks. It can use error correction, monitoring, resets, redundant modules, power isolation, or reconfigurable logic. If one inference is wrong, the system may repeat it. If one accelerator fails, the flight computer may shut it down and continue the mission in a reduced mode. NASA's Spaceborne Computer shows that the monitored commercial computing can operate successfully on the International Space Station. RadPC explores commercial FPGAs with redundant processing and background repair. But those demonstrations prove strategies in defined environments. They do not make every commercial chip suitable for deep space or crew-critical control. For more space systems where the hidden architecture matters, consider subscribing to Galaxial Frontiers, dropping a like on this video, or supporting us on Patreon. Let's talk now about how a new chip proves itself. A new chip still has to earn evidence. It has to earn its stripes. Ground campaigns expose devices to ionizing radiation and individual particle strikes. Then they test temperature, vacuum, vibration, shock, power behavior, interfaces, and fault recovery. Radiation beam time is expensive because the facilities are specialized and heavily scheduled. A useful campaign needs trained operators, dosimetry, custom boards and instrumentation, multiple devices, and sometimes even multiple manufacturing lots. Some of these tests damage or destroy the samples, and every operating mode or design revision can create another question to test. In-orbit demonstrations add the next layer. They show how hardware, software, recovery logic, power, and thermal control behave during real operations. But orbit is not a universal certification stamp. A successful low Earth orbit experiment may not represent a long deep space mission. NASA, ESA, chip suppliers, specialist laboratories, universities, spacecraft builders, and mission owners can all contribute evidence. A launch provider can offer access or a hosted payload. It does not by itself declare a processor safe for every mission. The mission accepts the risk, so the mission must decide what proof is enough. Now, why is the market starting to change? For years, proven designs won because the most demanding space chip market was relatively small. The cost of new silicon, radiation characterization, packaging, software, and qualification had to be spread across relatively few units. Using a trusted platform was often the rational economic decision. That history includes BAE's RAD750 line and the European LEON ecosystem, followed by multi-core devices such as the GR740. These are not frozen technologies. They show a gradual progression where architecture, tools, boards, and assurance mature together. Now, demand is changing. More spacecraft are being built. Constellations need larger quantities. Sensors generate more data than downlinks can easily carry. Autonomous missions and AI payloads need more processing on board. That creates room for different product tiers instead of just one definition of space grade. NASA and Microchip's PIC 64 HPSC is one roadmap. It combines 8 64-bit RISC-V application cores with vector processing, modern networking, security, isolation, fault tolerance features, and power control. NASA reported promising 2026 testing, including an early indication of roughly 500 times the performance of radiation-hardened chips currently in use. But that remains a test indication, not a universal flight heritage. Intel's Starfire announcement is another signal. The accessible public record points towards space survivability in advanced AI under size, weight, and power limits. It is not yet detailed enough to call the device flight qualified. The important fact is that a leading commercial chip company now sees this sector as worth entering. So why do space chips look 20 years old? Because the chips that dominated flight-critical systems were optimized for a market where reliability evidence, long support, and mission survival mattered more than rapid replacement. But the future is not simply faster versions of that same computer. Different architectures will serve different applications. Proven processors can continue to handle avionics and safing. Modern CPUs, FPGAs, and AI accelerators can take on payload workloads where their performance justifies managed risk. Supervisors, redundancy, isolation, and recovery software can connect the two of them. The market opportunity is to make that trust cheaper. Reusable radiation data, stable tools, supported boards, common software, hosted demonstrations, and qualification methods that do not restart from zero for every mission. Let's return to the AI satellite from the opening. Its advanced accelerator recognizes what matters in the data. Its proven flight computer keeps the vehicle alive long enough to finish the job. Neither architecture is obsolete, and neither architecture is sufficient by itself. The most capable spacecraft may succeed because engineers finally stop asking for one perfect spaceship and start giving each chip the job it can be trusted to do.